All right, we're going to look at another example of finding absolute extrema of a function on a closed and bounded interval. So an interval from A to B where the endpoints are included. So again, remember extrema are maximum and minimum values. And absolute extrema, as opposed to local or relative extrema, would be the highest of the high points and the lowest of the low points on the entire graph of the function, at least on the interval you're interested in. All right, and we have a theorem which says that if we have a function that is continuous on a closed and bounded interval, then we are assured that we do have an absolute maximum and an absolute minimum value of that function. So you might think a little bit about continuity of this function, where this function is continuous. I do have this fraction exponent, which is a radical. So you might think about rewriting this in this form, just to think a little bit carefully about whether we would have restrictions on the values of x that we could use in this function that would cause some trouble with continuity. Since this is a cube root, we don't have anything to worry about. You can take the cube root of a positive number, a negative number, 0. All of that gives output values. That's a continuous function. If we had a square root here, we would have some things to worry about, but since this is a cube root, we don't have anything to worry about. So this function is continuous everywhere, including on this interval. So we are assured that we do have an absolute maximum and an absolute minimum value of the function on that interval. All right, so we're going to go ahead and start by finding the critical values, or critical points, or critical numbers. So we're going to look at where the derivative is equal to 0 and does not exist. So first of all, we need to take the derivative. I'm going to use this form with the fraction exponents here. And you're going to need to use product rule and some chain rule. So the derivative of the first function, derivative of x, is 1 times the second part, this entire x minus 2, the quantity to the 2/3 power, plus the first function, x, times the derivative of the second part. So here's where we're going to need some chain rules if I have a function inside another function. So I'll start by taking the derivative of the outer part, so bring down that exponent, and subtract 1. 2/3 minus 1 would be 2/3 minus 3/3, so negative 1/3, times the derivative of what's inside that 2/3 power. So the derivative of x minus 2 would be just the derivative of 1x, is just 1. So I could get away with writing that 1 right there, but you need to think that through in case there's something else inside there. All right, so a very messy derivative in this case. But I'm going to start by thinking about where this derivative is equal to 0 and where the derivative does not exist. If I were going to take another derivative, I would prefer to leave it in this form with fraction exponents so that I could just do the bring down the exponent and subtract 1 thing. But when I'm thinking about doing the algebra to solve, or thinking about where this derivative might be undefined, I generally prefer to think about it in terms of the roots that these fraction exponents actually mean. So depending on what you were going to do next with this derivative, you might choose to leave it in this form, or you might choose to rewrite it. For the purposes of this problem, I'm going to choose to rewrite it. All right, so x minus 2 to the 2/3 power means cube root of x minus 2, the quantity squared. Here I have an x times 2/3, so I can make that 2x over 3, or 2/3 x. I'm going to write that as 2x over 3. And then x minus 2 to the negative 1/3, because that's a negative exponent, I'm going to have 1 over whatever the positive 1/3 exponent means. So 1 over cube root of x minus 2. So I can make this times 1 over cube root of x minus 2. Or then because I have two fractions that are times each other, I could just make this one fraction. And again, you can skip some algebra steps if you want, as long as you're not going to mess up the algebra. Okay, so if I were going to take a second derivative, again, I would leave it in this form. But because I'm going to do some algebra, set this thing equal to 0, and solve for x, and also think about where this derivative does not exist, that's why I would leave it in this form. Okay, so the first thing I'm going to think about here is where the derivative does not exist. You can do these in either order, but I'm going to think about that first. It's easy to forget about this one, so sometimes I do that first so I don't forget about it. All right, so remember the original function we talked about has a domain that's all real numbers. All values of x are okay in this original function. But if you look at this derivative, you might notice a root. It's the same root we considered at the beginning, though. Kind of talked already about why that doesn't cause any restrictions on x. The other thing I might notice here is I have a denominator. And so I have a root on a denominator, but the big deal thing here is the denominator. And that denominator would be 0 when x is equal to 2. All right, so many of the problems we've looked at, we haven't had any critical values that come from the derivative not existing. Every once in a while that has happened, but not too often. In this case, I do have a value where that derivative does not exist when x is equal to 2. So that's one of our critical values. And then the other thing I want to consider is when the derivative is equal to 0. So I'm going to set this derivative equal to 0 and solve for x, and we're going to have fun with the crazy algebra here. It's actually not too bad, but it looks kind of scary to start with. Okay, so there are several ways through the algebra here. The first thing I would notice is that I have an equation with a denominator. And so I usually prefer to start by multiplying through by that denominator so that it clears the fractions. I'm going to multiply through by 3 times the cube root of x minus 2. And so I'm multiplying that to both sides of the equation and every term in the equation. So when I multiply that to the left side of the equation, all that stuff times 0 is still 0. When I multiply that to this term, I'm going to have the 3 that's out front. And then I'm going to have the cube root of something squared times the cube root of that same thing. So this part will be the cube root of x minus 2 to the third. Because I have a squared here and then to the first power. So cube root of this quantity to the third power. So the cube root and the cube will undo each other. So here I will just be left with x minus 2, which is nice, because now I don't have roots anymore. And then again, the whole reason I'm multiplying through by this was to clear the fraction. So when I multiply this term by that, I really have this over 1, and you can think about that canceling. So we're just left with 2x. And thank goodness, this is much easier to deal with than this mess that we had before. So I guess my piece of advice here is to not get frightened when you have this horrible algebra. Just do a next step that you know is a correct next step, and then hopefully things simplify nicely after that. Often they do. It's just in the nature of what happens with the algebra once you've done product rule here. All right, I'm going to go ahead and distribute through. So I'll have 5x minus 6 on this side. I'm going to kind of combine some steps here to save some space. So add 6 to both sides of the equation. So I'll have 6 equals 5x and then divide through by 5. So I'll get x equals 6 fifths. All right, so I have 2 critical values. The next thing that sometimes I see students do is make that number line and test the sign of the derivative for where the function's increasing and decreasing. That is not wrong, but it's not going to get us to the answer that we need here when we are trying to find the absolute extrema. We need the highest of the high points and the lowest of the low points on this interval. So we need to compare the y values, the output values of the function. So at this point, at some point in the problem, at the end of the problem, you need output values for the function at any of these values that are in our interval. Both of these values are between 1 and 3, so I will use both of them. If they were not in the interval, then I would just discard them. If we were looking on a different interval, then included our critical points here. And then at the end points of the interval. So I need an XY chart. These are points. So these output values are coming from your original function. You need the end points of your interval, and you need the critical points that are in the interval. Those are places where the extrema might occur. Okay, so I'm going to plug these into the function here, and you want some simplifying or some decimal approximations so that you can compare these output values. All right, so when I put in x equals 1 to the original function here, I have either version here, 1 times the cube root of 1 minus 2, the quantity squared. So think about this part here. 1 minus 2 is negative 1, but when I square it, I get positive 1. Cube root of positive 1 is 1. times the 1 that is out here, so I get y equals 1. All right, when I put in x equals 3, I'll have 3 times cube root of 3 minus 2, the quantity squared. So 3 minus 2 is 1. Squaring that is still 1. Cube root of 1 is 1. Well, 3 times 1, we get 3. When I put in x equals 2, I'll have 2 times the cube root of 2 minus 2, the quantity squared. So that will be 0 times 2 is 0. And then for 6/5, I can't quite do the simplification in my head and get such a nice answer here. When we plug in 6/5, I'll have 6/5 out front times the cube root of 6/5 minus 2. So 6/5 minus 2 would be 6/5 minus 10/5, right? So negative 4/5. When I square that, I'll get 16/25. So cube root of 16/25, that's about as much as I can simplify it. You could rationalize the denominator if you want, but since these are not perfect cube roots, kind of stuck there. I probably at some point need a calculator to get out a decimal approximation for this so that I can compare. I need to know whether this number turns out to be bigger or smaller than 1. And it's maybe not so easy to look at this and determine whether that number is bigger or smaller than 1. So on my calculator, I already done that, and I've got about 1.03 for this value. All right, so what we're looking for here is the highest of the high points and the lowest of the low points on our interval. So absolute maximum, the highest of these output values is this. Absolute maximum is 3, and that occurs at x equals 3. And the lowest of these values is 0. This is the minimum value of the function, and that occurs at x equals 2. All right, so I've mentioned a couple times that it might be worth looking at this on a graph. We're going to go over to Desmos and look at this function graph and look at these points. Okay, so here I have graphed the function g of x equals x minus 2, the quantity to the 2/3 power. See, it's kind of a crazy looking graph here with a sharp corner at x equals 2. That's where our derivative does not exist. So our calculus work showed that, but here's what it would look like on the graph. And I've got a critical point, a place where I would have a horizontal tangent line. This is a local extreme value at x equals 6/5 or 1.2. And then the end points of my interval at x equals 1 and at x equals 3. I've made a little table of values over here that shows those output values. So just looking at that on your screen to sort of verify that the highest of the high points on that interval is over here at x equals 3, where y is equal to 3. And the lowest of the points on that interval is here at 0. The y coordinate is 0 when x is equal to 2. On a graphing calculator, you can restrict your window to the interval that we were started with here, 1 to 3. On Desmos, if you want to do that, the syntax is a little bit different. I'm going to go over here to where I have the function typed, and I'm going to restrict that. So I use this set notation bracket, and I'm going to write 1 is less than or equal to x is less than or equal to 3, and then close that bracket. And then it will restrict the graph to just the part of it that we were interested in looking at. And then it's maybe a little easier to see that in that interval, I've got my high point at one end, and I've got my lowest point here, y equals 0 when x is equal to 2. All right, we'll look at another problem that is a word problem in another video.